Okay, so where we left off yesterday was at the point where we were looking at the Newton's theory of gravity, in which Newton formulated the force between any two objects in the universe um, will be proportional to, let's start with that, proportional to the product of the two masses and the square of the distance between them, right? A proportionality is not an equation, and in case you need to convert the proportionality into an equation, you have to introduce what is known as a constant of proportionality. In general, this this is a particular kind of a constant, but we'll come to that, times m1 m2 upon r square. And it was also proposed, therefore, that this constant will be a universal constant, and that universal constant can be experimentally determined. Okay, so in today's class, we'll try to look at the history of this and understand how this universal constant was determined. Okay, so the whole equation was uh, sort of hinging on this factor that this universal constant would be discovered. And a great many scientists who came after or even during Newton's time set out to discover this universal constant. Okay, and the first thing that has to be figured out is how do we conduct an experiment to find out the universal gravitational constant. The challenges are many. If you look at this equation, you find that if we take any two masses, a few years ago, one senior school student in class 11 or 12, I don't remember, who was studying gravity, asked this question that, how come if the objects with masses are all objects with any mass are being attracted to one another, I don't see them sticking to one another. I don't see them moving towards one another. I place objects in a room, and when I come back in the morning, they are still wherever I left them. If there was a force that is acting between any two, so you see that it's not that a particular mass and another particular mass. It is any object with mass, any two objects with masses, right? So he said that therefore I'm unable to see for myself that there actually is a force between any two objects with mass. So I think the teacher who was dealing with him suggested to him that perhaps the forces are very small because the masses that we are considering are also very small. So he said, okay, I need to think about this. I need to check this out. So what he did was he came back the following day and he said that, no, I don't think what you're saying is true. Even if we take objects with one object being very small in mass and another object being comparatively massive, even then I don't see the forces acting. So the teacher asked him, well, how did you conduct that experiment? Did you do an experiment at all? And he said, yeah, I did an experiment. And what I did was I took a small marble. So I took a small marble, and he said I looked for the largest object that I could find which could move, which was a car. Okay, and he said that, well, I placed these two objects next to each other in my parking, and I allowed them to sit like that for the whole night. And when I came back in the morning, the place where I had marked the marble and the place where I had marked the car, it was exactly the same. I had expected that if there is a force, then the marble would have moved a little closer. So, so it was very hard to convince him that this equation is true. what do you think the student was missing, and what do you think the teacher could have told him to move him closer towards understanding the truth? Any suggestions from anybody? Yeah, Akshay, go ahead.
Sir, I think that the difference of the mass of the car and the marble is a lot. That's why the force was not working.
Uh, yeah, so if you think about the mass of the marble as m1 and the mass of the car as m2, what's the problem with that? There has to be a force acting according to these two, according to this equation. So there's a certain location that the marble has been placed, and there's a certain location that the car has been placed. So there is a distance between these two things, which we can call r. So there you have it. You have m1, m2, and r. And whatever there is, there will be a tiny amount of force. Whatever according to the equation comes out, there will be a certain amount of force that is going to act between these two. Why are the two objects not moving closer to one another? Janvi, are you able to hear me better now? So you can hear me, but you didn't catch it. Okay, I just explained it again. Okay, so the student was perplexed about this whole thing. If there is a force, I can leave it, and I can leave it for even a week. I can leave it for a month. They're going away on vacation. I left the marble and the car inside the garage for a month. They came back, no change in position, nothing. What was the problem? What could be the explanation? Let's put it that way.
Sir, I think the external forces which are acting on the marble for it to move is greater than the force acted by the car to attract it towards the car.
Exactly. So that's the problem that the student probably did not catch. That and this comes from the first law, right? An object will move only if there is an external unbalanced force acting on it. What if the force is being countered by, say in this case, it's very easy to know there is frictional forces, right? However you carefully you set the whole thing up, you're not going to do away with frictional forces. So that's one part of it. The other part of it is that even if you perform this experiment with very little frictional forces, the other explanation could be that the force of attraction between these two objects could be so small, right, that there wouldn't be any discernible acceleration that is possible. That is from the second law, right? The force is directly proportional to the the acceleration is directly proportional to the force and inversely proportional to the mass. So what if the force is so small that the acceleration, if at all there is one, is so small that it is discernible? And how could we set up an experiment in such a way that there is a discernible force that is acting between two masses? So that is why I took this example of the student asking this question. I don't know if his doubts about this were satisfactorily clarified. He was a particularly querulous student, so I'm not sure if he listened to all the arguments, but we can now move on to look at how the scientists at that time proceeded to perform this experiment. And I'd like to take up two experiments. Um, I prefer one of them, but I'll just mention the names of the people. One of them, of course, is Henry Cavendish. You must have heard of Henry Cavendish from your studies in chemistry, right? Henry Cavendish was in that class of natural philosophers who didn't think of themselves specifically as chemists and physicists as we do today. He was a genius of his time, that there is no doubt about that. And he was also what could be in today's terms called as a polymath. So there was a lot of different things that he was interested in, including mathematics. So he had an interest in animals. He had an interest in knowing more about chemical reactions and so on and so forth. And also famously, he was horribly, terribly shy. Uh, so much so that he probably maintained direct contact with only one or two individuals for most of his lifetime. It is said that he probably had not dyslexia. What is the thing when you are very shy and you can't directly deal with people? There is a disorder, right? I forget the name of the disorder right now. Somebody will remember, you will tell me. And the second one was, I think, a French naturalist, natural philosopher called Von Jolly. No relation to Jolsiaka. Okay. Autism, yes, Janu, that's right. So it was later figured out from the way he kind of conducted himself that he probably suffered from autism. We'll never know, but his behavior certainly seemed to suggest that he had that issue. In fact, there is no known picture of him or painting of him. There's only one, which is one of his closest friends drew, and he drew the coat separately and then filled his face out from memory. So if you Google Henry Cavendish, you will see that that single sketch as being the only reliable indicator of what he looked like. He was extremely wealthy and extremely smart, intelligent too. Okay, so so Henry Cavendish and Von Jolly were two prominent people among many others who attempted to conduct experiments to determine whether this equation held true or not. And the key to finding out whether that equation works true or not is to find out the universal gravitational constant, and then to know whether the universal gravitational constant holds true for all known situations. Okay, so I'll talk about Von Jolly's experiment. Henry Cavendish's experiment is also shown in the textbook on page 189 in the latest edition, but I'd like to look at it slightly differently. So the experiment was performed in this manner. So the setup, as I like to imagine it, okay, so this is not exactly how it was, but I like to imagine it like this. It must have been pretty close to this. So this kind of an setup is what is known as a torsion balance. And probably those of you who study physics into the senior classes will perform this experiment. So there's a very fine metal wire of some known gauge from which a bar has been suspended with two masses at each end. And these masses are similar in their constitution, as close as possible. Okay, so two tiny masses. And to the vicinity of one of these masses, you bring a very large mass. And I think in the case of Von Jolly's experiment, a large lead sphere weighing about 4,000 kilograms was rolled in. So if you're not able to understand any part of this explanation, do let me know, okay? So this was the lead mass. Are you able to understand this? So the torsion balance is there and the lead mass has been brought near it. The difference between these two masses are enormous. The lead mass was about 4,000 kilograms, and let's say the tiny mass was a few grams. Okay, maybe 5-10 grams, not much. So M1 is way lesser than mass of the lead mass. I'll just put it as ML. Okay, it's easy for me to keep writing that again. Right. So no, Akshay, not in the middle. So it's like you have to look at it as a three-dimensional rendering. The larger mass is placed near it, but behind it. Are you able to follow this? So if you look at it from the top, This mass is there and the lead mass has been placed behind it and not in contact. All right. So now, if there was a force of attraction between these two, you see the distance between this mass and the okay, let us distinguish this a little bit. M1R and M1L. So this is the left one and that is the right one. Okay. So you look at the distance separating these two. The distance between M1R and the mass of the lead and M1L and the mass of the lead, they are not the same, right? So there is going to be a small difference in the force of attraction between these two masses and these two masses, correct? Just wanted to check, there are a couple of people who just came in. Were you late or you kind of got logged out and came back in because of connection issues? So this is Apala was the last one. I don't remember who the other one was. Meanwhile, the rest of you think it through. Okay, yeah. Apala got logged out. So any idea, people, what's going to happen? You want me to explain the situation again? Okay, so the experiment setup is like this. There is a wire of known gauge, that means a known width, very fine wire. Suspended at the end of it is a rod with two small masses. The masses are very small in comparison to the large lead ball's mass. A large lead ball is rolled into the vicinity of this torsion balance, and there is a difference in the distance between this mass and the center of gravity of the lead ball, and this mass and the center of gravity of the lead ball, because of which there is going to be, if the equation is true, a difference in the force of attraction between these two and these two. What will that cause to happen? M1L is greater than M1R. No, Akshay, M1L and M1R are both of the same mass. There isn't a difference between them. So Neeraj is saying the right side mass will go down. Well, the heights of these are placed in such a way that they are all at the same height. See, because it's a two-dimensional rendering of something three-dimensional, I'm not able to show that. But M1, M1L, M1R, and the mass of the lead ball, the center of mass of the lead ball, they will all be almost at the same height. So they won't dip or anything, but something like that will happen. You're really close to the answer. Then why is the rod with the mass on either side not balanced? No, it's not. I'm showing it as not balanced. So because I want to show it in a 3-dimension. So they are not. It's not like they are balanced this way and this way. I'm just showing it so you can see that these two masses are in such a way that this mass is closer to that and this mass is further away from that. If it doesn't work for you, I can show it as a straight line, but then the distances I would not be able to illustrate. So that's just a choice of rendering that I have chosen for my drawing. They are balanced. Okay, to help you people along with this, we have just studied rotational motion. So strictly speaking, you should have been able to answer this question. So I have a seesaw, and I have this situation. So this person being more massive than this person has greater force of attraction than this person. So what will happen to the system? No, the whole thing won't go. I mean, the whole thing might go if the forces of attraction are large. But the problem is that the forces of attraction are so small that you won't have the entire torsion balance moving towards the leg bone. That doesn't work. It can happen. In fact, there is an interesting story of when that happened, but I'll tell that a little later. Remind me. It's the story about measuring the height of the Himalaya, the Mount Everest, that is. Yeah. So now you see the connection, right? So you're going to have a sufficient clockwise torque in this direction to cause a rotational motion to happen, right? So why not the same thing will occur there? You get it? So there is going to be a rotation in this form. So it's not going to rotate like this, obviously that's not going to happen, but it's going to rotate like this. The mass m1 will move closer towards the lead ball. Okay. So now Neeraj sees it. Does everybody see it? Any questions? You did not follow the arguments closely. Do you want me to repeat anything? Nandan, would you want me to repeat everything once? No, okay. Thank God. So what has all this got to do with the equation? How did that help anybody to find the value of universal gravitation? Can somebody cut through to that? So you have a torsion balance, you have a huge mass, you have a small mass. The torsion balance turns because of the torque. You see, that's why the word torsion. There's going to be a torque that is created because there is a slightly greater force on one side in comparison to the other side. So I'll add one more to this. Probably something to do with the speed. Man, that's the whole point, right? The forces are so small that the acceleration is indiscernible. We are talking about somewhere in the late 1600s, early 1700s. They had no way of figuring out what the velocities would be when you looked at such small movements. Okay, so Akshay is saying, so rotation will stop when the distance from the lead mass to both of the small masses is the same. So the force on both the small masses are the same. Well, yeah, you would expect that if the force is large enough to continue the object to move, but no, that was not the case. The forces are very small in this. Okay, so actually I don't know that even visually will you ever be able to see any movement, but something interesting happens because this wire is an extremely thin wire. What would happen is that wire would be subjected to a torque as well, right? So it would twist ever so slightly. Whether you are able to see the movement of the masses or not, I am not sure, but apparently you are able to see a tiny twist in that wire. That's a very, very, very thin wire. Okay, just so enough that it can support the mass that is there at the bottom. So what do we do with that twist? Any ideas how we could proceed from there? So I just wanted to check with Syed. So Syed has studied physics up to university, I think, and I was wondering if you have any thoughts about what we have spoken about so far. Yeah, Neeraj, you're thinking in the right direction again. Yeah, go ahead, Syed.
Like I'm thinking about the twist may happen.
We are not able to hear you very clearly. Yeah, that sounds better.
Like the twist, the string which you are using, there will be a twist.
Yeah. So no, I'm not asking you to answer the question. I'm saying, are we proceeding in the right manner to figure out the answer to the question about the gravitational
Yes,
constant?
yes.
Have you heard of this before?
Yeah, we have
Okay.
we have gone through the formulation which you have written there on the left top, but we have even heard about the Henry Cavendish experiment. And this one is quite new for me.
Okay. So you have studied this. You must have also performed the torsion balance experiment, either in
Yeah,
high
we have
school,
done our in our UG level.
in your UG. Okay.
No, in UG.
Okay. Right. So okay, so we'll proceed then. There wouldn't be, yeah, so you're all thinking, right, the wire is going to twist, and it's not going to be a big twist, because now you understand that the difference in the forces are going to be extremely tiny, but the twist is nevertheless there. Okay, now the thing is, if you know uh, how much force is required to twist this wire, okay, from independent experimentation, from some other kind of experimentation, you apply different amounts of forces to the torsion balance, not in this experiment, otherwise, right? Then you could also then plot a graph, right? You could plot a graph of, just for the sake of convenience, I can put force and twist, okay, let's say in the x-axis and the y-axis. So I apply large forces. We are not talking about gravitational forces. We are going to physically apply forces, right? So you will plot, you will say, okay, let me apply 4 different kinds of forces and see how much twist is going to happen. And you'll see that the twist increases, right, as you increase the amount of force. So from this kind of an experimentation, what you can figure out is that there is a linear relationship between the force and the twist. It may not be a linear relation, but for sake of simplicity, we'll take it as a linear relationship. It's most likely to be a logarithmic relationship. But you can then project it backwards, right, to say it won't go behind this, because the force cannot become negative, but you have to move the y-axis a little bit more. So what you can see is that as the number of amount of the twisting reduces, I'll just move this y-axis, if you don't mind, to somewhere here, right? What you will find that as the number of twist reduces, the force that is applicable also reduces. So what you can do is you can then find out, model an equation for which, if you know the number of twists, you can work out the amount of force that has been applied to create that twist. Yeah, you won't be able to plot an actual graph. Akshay is asking a question, how can you do that on a graph? No, you can't actually do it on a graph, but you can model an equation which can then tell you, if you keep reducing the number of twists, right? I suppose they must be looking at it in terms of angle. For what minimum twist, or for what level of twisting, what amount of force would be required? Are you able to see this? And then you can work out a chart, right, which says for this amount of twisting, this amount of force is applied, and so on. And now if you put the two things together, what do you get? You need to be looking at the equation. Look at the equation and think of mathematics. No, Akshay, they don't need to move the lead mass anywhere. All I need to know is what is the twist on it. Okay, nobody is asking another pertinent question. There is another pertinent. Yati, it's nothing. The balance is just that there is a very, very thin wire, rod, two masses, and they are free to twist. That's all. That is what is called as a torsion balance. It's a balance because it allows you to compare forces. Okay. So one practical question that can be directly asked from this, because we are running out of time, is that how do you measure the amount of twisting that can happen? Okay, and that's going to be really difficult because the forces are extremely small. So what can be done is you could place a tiny mirror over there. I believe this is possible. Okay, and in fact, I believe that it was done like this, and a light source was trained on this mirror. Okay, so what will happen when you focus a light source onto that mirror? Reflection, of course. So you are going to get a reflection of this, right, which you can then place on a scale. The scale can be in terms of distance, it can be in terms of the degrees of twist, or you can also interestingly place it in terms of force. It's just a matter of calibration, right? You can put anything that you want on that. And now if you perform the experiment, when the torsion balance twists, you are going to get a movement in this, right? And that movement between here and there is going to tell you how much force has been applied. Okay. So now coming back to the equation, and I have to stop now, so I'm going to quickly go through this. We'll cover the rest up when we meet on Tuesday, and maybe you can come back with a specific idea of what could have been done. In fact, I won't lead you to it also. I'll leave it as it is. I'll say, having performed this experiment, how can you find out the value of K? Think in terms of equations, think in terms of algebra, think in terms of LHS, RHS, changing the subject of the formula, etc., etc. And tell me, by performing this experiment, how did Cavendish and von Jolly arrive at an estimate? Of course, it was just an estimate of what the forces, what the gravitational universal constant was. Okay, so for that we will meet in the next class. I just wanted to remind people that Perumal sir said that he will be meeting those who are working on the the Python class. Apparently some doubts and questions were there. Manya was supposed to be joining this group, but she's not even here. But anyway, I was asked to remind you all, so I'm reminding you for that. Okay, so we'll stop now, and we'll meet again on Tuesday. Think this through by Tuesday. I want the solution from one of you. If you want to email me about the discussion, you can do that, and we can pick it up from there. All right, then, see you on Tuesday.